Hello, everyone. I'm Emily Fox. Thank you so much for taking the time to join me today. I'll be talking to you wonderful people about knowledge glaciers and the disappearance of institutional knowledge. I'm available for Q&A throughout this presentation, so don't be afraid to jump in and ask questions. However, before we get started, I wanted to cover some base rules. I do not possess a degree in knowledge or history. My degrees are in information systems and cybersecurity. I'm also not a computer scientist, software engineer, or system administrator. I'm a security person through and through. The information I'm going to discuss in this presentation is derived from over a decade of industry and government observation, reporting, and research. They are not an official position of my current or previous and past employers. Many roles, industries, and organizations are discussed in this presentation. One is not better than another, and I intend to present the actions and effects of each of these in an observational manner, focusing more on the knowledge impact and the impact to security. So let's get started. Knowledge glaciers are real, and they are melting. If you don't know what a glacier is or may have forgotten elementary science, here's a refresher. A glacier is a slowly moving mass of river and ice formed by the accumulation and compaction of snow on mountains or near poles. And they're melting. Scientific research has shown the overall mass of glaciers on Earth is reducing at an alarming rate due to environmental factors beyond the glacier's control. This should sound vaguely familiar to you, as it seems like nearly everything that happened in 2020 is beyond our control. According to the National Snow and Ice Data Center, or NSIDC, glacial ice often appears blue when it becomes very dense and free of bubbles. Years of compression gradually make the ice denser over time, forcing out the tiny air pockets between crystals. When glacial ice becomes extremely dense, the ice absorbs a small amount of red light, leaving a bluish tint in the reflected light, which is what we see. This means the oldest and purest parts of the glacier are the bluest. So what does that have to do with knowledge and security? Well, there's these things called knowledge glaciers. They are the accumulation and compaction of deep knowledge built over time that provides foundational understanding as community knowledge expands in a particular area or around a particular technology. And guess what? They're melting too. The advancement of technology, expansion of automation, consolidation of expertise, and many other factors are reducing the amount of and the completeness of institutional knowledge being transferred from one technology generation to the next. Over half a century of technology expertise have forged glaciers of knowledge. Accumulating and transferring this dense mass of knowledge is difficult and hard to successfully perform within a team, let alone an entire community. Years of knowledge compression have gradually made the depth and breadth of knowledge denser over time, forcing out the tiny, time-specific and application-specific pockets of knowledge between innovation bursts. What remains is a pure foundation of knowledge from which innovation is born and then commoditized. Now, as with glacial melt, there are environmental factors to consider. Expected productivity and velocity. A culture of curiosity that generated innovation and upheaval is disappearing. Knowledge gained is evaporating because we are so busy trying to move forward faster than everyone else. This leaves security in the dust for teams without a security Sherpa. For technologists to be productive immediately, they cannot act on the information to make informed decisions, just as security practitioners often apply security requirements without enough information to determine their feasibility or even applicability. It's checklisting and moving on. And this technologists are being herded en masse to produce an object, a thing to be the cash cow of an organization. If it's not making cash, how is it helping to make cash? Career alignment. Career goals are tied to product delivery. A lot of individuals see the success of developer advocates and big personalities in open source as the alignment of stars for where they want to be. They see the product launch of a highly enviable project as the trajectory for their own personal success. Some in the community even hunt for the next cutting edge innovation to either launch them into stardom in the community or wealth to move on to the next big thing. Organizations even encourage them to this model of thinking because it drives product development, further feeding that cash cow. Organizations today need to reach beyond Horizon 1 to Horizon 2 and 3. But in reaching these goals, organizations end up trampling on the knowledge and growth of the individual to get there if they do not carefully nurture their continuation and advancement. Cloud. The birth of utility computing, or as a service anything, in the early 2000s shifted industry away from self-management of hardware, power, space, cooling, racking and stacking, cable management. As with most As with most innovations, security is only now beginning to catch up in this space. Technology companies attempting to offer utility computing began to sweep talent pools of highly skilled, experienced, and costly individuals to make their offerings more robust, more resilient, and competitive with this emerging market. Companies that began adopting as a service to reduce their IT costs ended up decreasing local demand for hardware engineers and administrators, and therefore the needs have shifted again. Few reinvested in these human assets to keep institutional knowledge and expand relevant skills. This moved labor needs to service providers, ultimately consolidating infrastructure management knowledge and leaving an entire formerly desired community to abandon and suppress knowledge and take up a new tradecraft or evolve to meet the new market demands for which very few had expertise in outside of the service providers. Automation. Cloud service providers themselves have felt the IT cost burden and have been increasing automation to continually lower overhead costs and increase revenue. Automation of orchestration consolidates more knowledge and further dilutes the skills, history, and expertise for which its manual antecedent was created. Automation does many amazing things, however. Manual processes and procedures that used to be error-prone and probably still are can now be defined and exercised repeatedly and with the same expected result. You do it once and it is applied many times over throughout an entire enterprise. That knowledge, however, about why we do it a particular way is not captured in this automation process, simply the manner in which is being used to accomplish the feat, not the reasons behind it. The vast majority of developers assume the next person to read their code is just like them, and therefore their comments are lacking or not intelligible. If a section of code was deleted, most organizations would not understand the impact based on the comment within that section. Moreover, most code is not even revisited, but commented out and left there to be manipulated at a later date by a potentially malicious actor, or inserted following the same comment out pattern to play a waiting game before adding it back in. Cloud service providers, in an effort to protect themselves from their customers and their customers from each other, institute layers of specialized controls and abstractions, limiting just how much you can tweak and configure their offerings. They need to make it easier and faster for their customers to move on to the next big thing without having to spend time, energy, and effort researching all the nuances of a particular product. And their customers want this. In many cases, the manner and mechanism by which this is performed is kept confidential and proprietary because the methods that enable the level of abstraction can provide, and in many cases do provide, market advantage. This makes it extremely difficult to understand how a cloud provider is meeting compliance, security, and regulatory requirements. Aside from a certifications body such as FedRAMP or a certification standard such as FIPS 140-2 being attested, consumers are left to trust but often unable to verify these claims. So we're at a point now where you're probably wondering why the security person is talking about knowledge and glaciers and early technology. It must have something to do with security or even modern technology and where we're at today. So there are 2 points that I want to have you consider, and they're interwoven throughout this presentation. So be mindful. Without knowledge, we cannot be informed. If we're not informed, we cannot be secure. Consolidation and automation make security life easier. Consolidation and automation without transparency can obscure and inhibit actual security. Security professionals and technologists cannot just know they're part of the development cycle or their fiefdom and be done with it. We must also have knowledge of the technology, how it fits into the bigger picture, the history of the technology to a certain extent, how it arrived here, historical vulnerabilities for it, because inevitably someone will fail to implement a regression test for at least one of them. If we're not appropriately informed about how functions work and why it is done, especially why, we cannot make appropriate recommendations to mitigate, resolve, or transfer risk. This is the exact same thing that project teams need to understand before they can begin developing a product. Identifying what the actual problem is before we can design a product to solve it, and identifying what the product will do in order to secure it. While consolidating reporting streams and automating a lot of manual processes like account creation can make our lives easier, we need things to provide context around those vulnerabilities we are seeing in a dashboard. If an exploit path is present, or if there are active or mature exploit in the wild, for instance. And we need to know what the basis of that context is, because what we see is often difficult to discern relevance from, and we end up relying more on the automation to do our jobs than the actual skills that enable us to do them. Here's an example to scare you. They didn't fully understand what was happening amid a confusing cacophony of warning alarms and alerts. They could not regain control, killing a total of 346 people. This is an excerpt from NPR digging into why two 737 MAX airplanes crashed. It turned out Boeing's flawed design and a new automated flight control system was a major contributing factor. We can destroy lives if we fail to take the time to understand. Think about this. Without having transparency in how automation works, understanding what it is showing and where things are coming from, we can destroy lives. The more we automate without transparency into how the automation works and without taking the time to understand it, we're losing valuable skills and knowledge that may eventually be catastrophic to another human being or even the planet. And as we've seen in the above case, we need to pay attention and we need to make changes, but we cannot make changes until we understand how we got here. Our technology history is steeped in research and defense, seeking to understand and seeking to secure. How have we moved so far from this? We've lost our curiosity as a community and the culture that it cultivated. Individuals spend months exploring the vast complexities of revolutionary computers and networks, learning how they operate, interact, and how they can be exploited. Retaining, sharing, and publishing any details learned enable collaboration and breakthroughs only accomplished by building on decades of knowledge. This corpus of knowledge, a glacier, if you will, is the basis by which modern technology upheavals were born from. The commoditization of innovation, the building of more complex, higher order systems significantly reduces the learning curve to use each new capability because we assume that the knowledge gained to develop it is imparted on the generation using it. We also assume that it has performed due diligence for security, and lucky us, we get to inherit all of their hard work. But unfortunately, this is not always the case. In order to win World War II, we needed to increase the input and processing of the existing computers we had. They were human at the time. IBM's ASCC, otherwise known as the Mark I, along with other electromechanical computers, were designed to solve advanced mathematical physics problems to support the war effort. Soliciting knowledge across multiple federal and non-federal groups, the US was able to modify and improve upon the ideas of the EDVAC, Mark I, and eventually the UNIVAC. The need to increase speed and better tests for inputting data into this equipment led to the creation of the A-0, A-1, and A-2 compilers, which then led to the concept of keyboard input and then Fortran. These were the major innovations in a long line of innovations, and for the purposes of this talk, we'll start here. What were the innovations from the 40s and 50s? The methodology of writing code or software development was a byproduct of getting more accurate results from the Mark I. The concept of reusable memory was exercised. We see programming tests being literally written and then encoded to ensure the machines are configured correctly, and the concept of compiling code to enable more efficient use of the computer. As we continue to build on the success of electromechanical computers and many other technologies from that time, we are beginning to see computing take hold as a potential commodity. Technologists in the 60s and 70s realized we needed faster ways to communicate with this new medium, and thus began the era of telecommunications. ASCII, BASIC, Unix are key innovations here, but continuing on that collaboration idea, ARPANET becomes the internet and emails are now being sent. Pong has officially made its debut. Thanks to Apple I and Apple II, personal computing has potential, and we see text-based RPGs begin to make an entrance. The innovations of the 60s and 70s were email, the ability to send a message and receive a response faster than the postal service, the internet or intranet connecting more and more people every day, the concept of computer gaming, that computers can be used for more than mere calculations and can provide an entertainment value, microprocessors that enable computers to do more than just one thing. With telecommunications now being a largely expected presence for the future of any organization's success, we are seeing network systems become the next commodity, enabling technical play and a rising counterculture looking to poke and pry at these existing wide open architectures built on implicit trust. With more people owning personal computers and getting online or passing Laserdiscs and now CD-ROMs with games on them around, curiosity is beginning to push people to test the limits of this new playground and discover, using it in ways that the creators had never thought. Do you think that Grace Hopper or the US Navy would have ever predicted that Mark I's ability to calculate trajectories to support a war would contribute to a community focused on entertainment? In the 1980s, the Morris worm began to wreak havoc on the internet. The first felony conviction of the US happens as a result underneath of the 1986 Computer Fraud and Abuse Act. Industry and government are beginning to pay attention to the counterculture that is growing in the internet and freakers wreaking havoc in these wide open, insecure telecommunication systems. The innovations of the 80s were better memory. Floppies, CD-ROM, flash, they all contributed to our ability to continue refining and making computers more powerful. Word processing enabled more efficient and consistent communication within and across organizations. C++ was created, and computer security awareness finally appears in the media for the first time. Everyone is now getting online, and companies are seeing a new space, e-commerce, to increase revenue and reach new markets they didn't know existed. A growing need for security experts is becoming apparent. The internet is now the commodity. In a rush to tap into e-commerce, potential companies began purchasing compute. They bought space, they hired people, they needed tons of admins and developers to bring their brick and mortar presence online. And many of those individuals came out of that counterculture because they were the only ones with the knowledge of how these new systems and networks ran. We can see skills like system admin, network engineer, and server hardware technician become some of the highest paying and highest demand jobs in the market alongside developers, but we also see configuration drift making its first appearance. Companies needed the flexibility to make their online presence possible, and with that counterculture of freakers and hackers now becoming professionalized, we begin to see more open source use. Innovations in the 90s, Linux, arguably the most widespread and most used open source project. Web browsers enabling internet access for companies and consumers alike. Wi-Fi enables technologists to move about free from wires and still be online. Online transactions, getting paid electronically for goods and services rendered, and Java, still one of the top languages in use today. Companies are now beginning to feel the pain of these IT gains from the 90s, some making the drastic jump to create utility computing, seeing this as the next need by industry. Automation and skills consolidation that I talked about earlier are happening now. We begin to see the knowledge loss and skills abandonment. Organizations begin to shift and offload their technical debt in favor of outsourcing homegrown, unsustainable solutions to companies arriving on scene that can solve those problems for them because of their specializations. Teams focus more on doing one thing well, really well, and selling this as a service. The beginnings of career and product alignment appear as individuals begin to deep dive on major problem areas. Agile and DevOps make an appearance and gain a following as more and more companies realize waterfall development is not sustainable for reacting to market changes. Teams are relying heavily on their most senior person, as Ian Coldwater put it, recognized by the epic beard or fabulous hair, to come in and save the day and then disappear in a cloud of smoke and fire when your metrics, if you had them, started flashing green again. What were the innovations? Utility computing. It only exists because of the networking languages and compute that came before it. DevOps, recognizing silo teams cannot enable high velocity product delivery, and Agile, a better way to develop software. And these are all great things. We have done so much. The world isn't on fire. It probably is, but that's not the point of this talk. Consider this. In order to work on the UNIVAC 1 in 1951, you had to have an advanced mathematics background and experience in a very exclusive field. Today, you do not need to know the fundamentals of networking to create an e-commerce site in AWS, or even be strong in any programming language and not even know a programming language. We've made it this easy. But what's the cost? In the past and even today, highly specialized capabilities require in-depth knowledge to fundamentally understand how they worked. This specialized knowledge generally means there was a lack of focus on security. The configurations of these capabilities were to optimize them to do the one thing that they were designed to do. Attacks in this area therefore required equal knowledge specialization in order to successfully carry them out. Usually this meant time to learn and understand how the object worked. More commonly today is this generalization intercompatibility of components. This lowers the barrier to entry because technologists don't require their users to understand fundamental concepts of how software or systems work. They can get started and deploy easily. This means the default settings are insecure, as security often delays lead time to deploy, ironically, because it's not the default behavior, and would require the user probably to understand not only how the product they want to use works, but also how the remaining parts of the architecture work. And let's be honest, no one has time for that. Because we've made it so easy for people to use, that means that there are more instances of insecure by default, which means an attacker just needs to exploit one area to be able to impact hundreds or thousands. So while the complexity of the attack is gone, we've now increased the volume and spread of the potential attack. Nothing is really more secure here. Effectively, you have to choose between making it incredibly hard and unappealing for the attacker because you have to know the ins and outs of all of how everything you have works and therefore have to commit more time to exploiting you, or you end up biting the bullet and just know that you're going to get your product owned in some capacity, but you did your best by at least making security an option in the configurations for your product. So let's talk about SCADA and infrastructure systems. Organizations and governments are looking for any and every way to ease their job and save money. If they can make it easier to do X, then I can focus more on Y. Or if I can save X because we can outsource the security requirement, then I can apply that to Y for next quarter. We see this through the adoption of smart grid technology, remote access enablement on workstations, and the continued interconnectivity between consumers and suppliers. This means we've taken the security headaches of prehistoric technology and modern technology. Lack of patching, poor access control, credential compromise is still very popular, all of those things, and applied it to the lifeblood of humanity: food, water, and shelter. And when you talk about SCADA specifically, only 10 to 20% of organizations install patches that their SCADA vendors are releasing because a power cycle or a shutdown is required to apply them. And nobody wants to be at fault for a service interruption. By introducing more levels of automation, new generations of operators won't be aware of how to perform a manual override. This lack of knowledge that I discussed previously and understanding how the information system is supposed to work and how we're supposed to protect them is a cybersecurity risk. This goes the same for operators. If operators fail to understand how the automation is interacting with their components, it's going to be a matter of when, not if, an attack occurs. Can they limit the damage? In 2015, after 6 hours and a loss of over 130 megawatt load, operators restored power by sending technicians to substations and manually controlling the power system. Because they knew how, they pulled all the SCADA systems offline and went into manual mode, which was the only way that they could restore power. The lack of complete knowledge from the automation systems required the Kyivoblenergo to rely on their call center, which was subject to a telephone denial of service, giving them untrustworthy information to pinpoint and respond to outages. And since the HMI was offline, the backup system, which was their telephones, was unable to assist them in bringing power back. More recently, attackers successfully manipulated the levels of sodium hydroxide, or lye, in Oldsmar, Florida water treatment plant. The engineer initially dismissed it because his boss often connected to the engineer's workstation to monitor the facility system. If you're not cringing at this point, you probably should be. The engineer had been trained to normalize remote access from an unknown entity. 5.5 hours later, the cursor began clicking through the water treatment plant's controls, again considered normal behavior by the boss, until the attacker changed the level of lye and was seen. What if the attacker had also happened to override the automated pH testing safeguards with false data, similar to pre-recording security footage to play while you pull off a heist? Would the engineer have been able to detect the override, know it happened, even able to revert the changes had they not been in front of the workstation? We are relying a lot on the tools we use to work properly. We make assumptions and provide implicit trust on what was sold to us. When they break, there are very few individuals who know how things worked before those tools were integrated, or why we choose those tools, and a lot of them are nearing retirement. In less than 30 years, we will have lost most of the generation that gave us Netflix, Baracode, and Back Orifice. This is where we are at. We've got developers cranking out code, using build kits and pipelines to make their lives easier so that they can deploy their ideas to production. But do they know how to verify or even reproduce their builds to detect malicious insertion, such as has occurred with SolarWinds? We've got admins and operators cranking out those same scripts and watching the beautiful, colorful charts for monitoring all of their services reporting green with no error codes. How many of them know what those metrics are actually looking at to determine green, yellow, red, or death? Or independently verify that they aren't being falsified? Or what that script they copied from Stack Overflow actually does? Where that dependency came from and what else is in it? This is a struggle. balancing velocity with knowledge to overcome risk. The epitome of security is knowing as much as you can about what you have, what you will have, what you don't have, so you can implement a balance of security controls and compensating mechanisms to ensure your data or your customers' data isn't plastered all over tomorrow's news headline. Take the supply chain. Do you know where that library actually came from? Are you sure you spelled the package name correctly? Is that really your build running in production? In the age of Kubernetes and folks getting fancy with their names, it makes it easy for your team to be owned in a typo squat. We cannot expect developers and operators to know everything there is to know about security. We can't send them back to college for another security degree. We only have so much room in our own personal knowledge base. Something has to go. And for most of the technical community, if it's not something that they do every day or even every week, it gets lost. That glacier starts to melt. It becomes knowledge icebergs. Developers don't secure applications. They build and ship them. That's what they do. So how do we enable ourselves to innovate? Build on the knowledge of others in an informed and transparent way. How do we ensure the security of what it is that we're building? As institutional knowledge disappears, these glaciers melt and break off. They form knowledge icebergs. Layers of abstraction in our information systems and architectures are designed to create defense in depth and security barriers, as well as enable developer teams to focus on what they specialize in, creating new products and services. If we were to apply water density principles, how icebergs float here, about 10% of knowledge needed to create or innovate is institutional or deep technical knowledge. When used in this capacity, it is considered passive, understanding how it works, seeing beyond the horizon. 90% of the knowledge used is in daily tasking and implementation details. When used in this capacity, it's active. This is the practice of commoditizing a thing and working through that on a day-to-day basis. But when a crisis occurs, such as a cyber attack, those values flip. Our active knowledge must become 100% to inhibit or revert an attack. We have to understand how the system actually works as well as how we think it works, which is usually a result of abstraction and automation, in order to estimate what else could have been tampered with. If you fell asleep and are completely lost about how to save the knowledge glaciers, don't worry, I've got you. Nurture the people you have to expand their skills. Do not abandon them. You need them, whether you realize it now or not. They provide a unique experience and can diversify your way of thinking, as well as provide you with the information you need to make better security decisions. Encourage your teams to learn together. No one individual can be responsible for successfully relaying institutional knowledge. Not everyone is a born educator, and some people don't like talking. That's okay. Give them opportunities that suit them to collaborate and shine. Documentation is important, but making documentation accessible is the most important. Easy to understand is the second. We cannot save knowledge if we cannot find it or even understand it. This means making it available in multiple languages and in multiple different avenues. If someone took the time to write it down, it needs to be read. Make the time to read and encourage others to do the same. Find the balance between velocity and knowledge, and we can save the knowledge glaciers. You need to engage in systems thinking. Understand it end to end as much as you can, and don't be afraid to ask questions, because inevitably the amount of time it will take you to discover the information needed to resolve a crisis is more panicked and stress-inducing than if you had just had it in the first place. This is what makes teams employing chaos engineering so successful. And if the documentation sucks, submit an issue and take the time to be specific and provide a recommendation if you can. The extra 5 or 10 minutes you spend explaining it as a security professional or as a developer or a system admin will save somebody else an hour of trying to understand what it is you are attempting to explain. We need to promote and cultivate a culture of continual learning and experimentation. We've lost it and need it back if we want to continue to innovate in a secure fashion. We need to accept the challenges that come with this and enable changes to make it safe to fail fast and stop normalizing bad behaviors. I've talked a lot about a bunch of different topics today. I have references available to you on this slide if you're interested in learning more, reconfirming any of the information that I have presented. I cannot take the time to stress enough understanding how these things work and sharing that institutional knowledge is key to a successful and healthy security organization and security culture. Thank you so much for your time today.